Hello to all. We had a wonderful camp and an amazing contest last night, and now we are here to discuss all the problems. So, we will go in the descending order. Uh, Along with me, there will be Manak and Subham to discuss all the problems. So, Manak will start from basically F, G, H, and then Subham will do basically C, D. I will be taking A, B, E. So I think we can begin the session and we can start with the discussion. I think I should introduce. Manik is currently master on Codeforces. He is from IIT Kharagpur. Along with us, we have Suham. He is from IIT BHU, currently expert in Codeforces. So it will be an amazing discussion session, and we are marking the end of the camp here. So we can begin the discussion. Hello, Manik. Am I
Okay.
audible?
Hello. Yeah. Hello, everyone. I'll be discussing F, G, and H, the three artist problems. So we'll start with F. Uh, so the problem was you're given a tree and you have to calculate this quantity. So for all pairs of vertices, you need to calculate the powers of the distances for the 0 p less than equals k. So, for example, the first example was you're given this tree, right? So the distances would be d11 equals 0, d12 equals 1, d13 equals 1, d21 equals 1, d23 equals 2, d22 equals 0, and then d31 equals 1, d32 equals 2, and d33 equals 0. So these are your distances in the tree, and now you can need to calculate the pth powers of these, the sum of those. So we'll have the convention that 0 to the power 0 is equals to 1. So working with that convention, um, if we take p is equals to 0, first let's count how many of each number we have. So we have uh, 1, 2, 3. So 0, 0 occurs 3 times, then 1 occurs 4 times, and 2 occurs 2 times, right? So if you want to calculate this value, we can just sum them up. So we'll have 3 into 0 to the power 0 plus 4 into 1 to the power 0 plus 2 into 2 to the power 0. And this is just equals to 3 plus 4 plus 2, which is equals to 9. And then p is equals to 1. That one is this quantity. And if you calculate this, you get 8. 4 plus 4, 8. Then p is equals to 2, you get 3 into 0 square plus 4 into 1 square plus 2 into 2 square. So that's 4 plus 8 equals 12. So that's how the first sample is working. Now, to solve this problem, you need these topics. You need to know 3DP. You need to know binomial expansion, and you need to know rerouting DP, which I will explain all of these as we go. So let's just say we want to solve it for a single node. Okay. So let's say we have this tree, and instead of calculating it over all pairs of vertices, we will just find distance from this to this to this, and so on. Right. So to do this, we can use DP, right? So let's define our DP state. This is the root. Let's define our DP state as DP u comma p, and this is equals to sum over v belonging to subtree of u, uh, d to the power p of u to v. Okay, so how do you calculate this quantity? So let's say U has some children. Okay, these are U. Now U has some children C1, C2, and so on. So if we want to go to a node V, we will have to go through one of these children, right? So basically, we can write that dp up is equals to sum over. Uh, so if you want to get to V, you have to take the path from C to C1 to V, for example, and then you have to go U to C1, right, to get from U to V. So basically, what has happened is we have added this one extra edge in our path. So that means the length will change of this path, right? So we can write that. So we'll sum over each child, the children of U, and then we'll sum over V belonging to subtree of C, and we'll calculate this dc comma V plus 1 to the power p, because we have added this one extra edge over here, right? So now this thing, you can actually do binomial expansion on this, right? So what do you get? You get sum over children of, I'll just abbreviate it as CU, sum over V belonging to SU, subtree of U. And then the binomial expansion would be K equals, I'll use something else. I'll use J equals 0 to P, Pj dCV to the power j, right? Now, this we can bring inside, right? We can swap these two summations because this factor is not dependent on V. It's not dependent on V. So we will write it as sum over C belongs to CU. Uh, j equals 0 to P. Then we'll bring this outside, and inside we will write V belongs to SU of d to the power j CV. And now this quantity is the same as this thing, right? It's basically dp v comma j, right? So that means our dpu uh, p is equals to sum over the children, and you will get j equals 0 to p binomial pj times dpvj. So this means you can calculate, right? One thing I missed was that when you add this u here, then we are considering all values in the subtree of u, right? Now u is also in subtree of u. That means we also need to add this factor. We need to add d to the power p of u to u. But notice that this value is it's going to be 0 if p is greater than 0, and it's going to be 1 if p is equals to 0. So this factor you will add, and this will take care of the base case. Okay, if you have a leaf, then you will only have this factor. But this is like an extra factor that will it'll make our calculations a bit messier, so I'll ignore it. Okay, but remember that it exists. So now you can calculate dpup for a fixed u. So that means we have now successfully used 3dp and binomial expansion, right? But we need to calculate this over all possible values of u. That is, over all the nodes, we need to calculate this, right? Since our original problem was calculating over all u and v. So now, if you try to, the complexity of this solution will be something like um, O of n times uh, p or p square, right? Something like that. But p small, so it doesn't matter really. But the point is, key if you try to run for all nodes by brute force, then you will run this n times, right? So that's bad because now it's O of n square. So if you have O of n square, then it won't pass because n is less than equals to 10 to the power 5 or similar, something like that. Um, so the way we will solve this problem is that we will reuse our dp values, and we can do that by we will use something called rerouting. So what is rerouting? It's just that, say you are at u, okay. Now we will try to find the answer for some node that is adjacent to you, say v, right? Now we already have all the dp values for v subtree and then u's entire subtree. So now if we made v our root, then we would have a situation that looks something like this, right? So how do we go from this to this? How do we go? Now notice that we can do this thing. What we will do is we'll update our answers like this. So first we will take u and v, we'll have this, right? And then we will detach v and we will update our answer. So now we have u and we have v. These are separate. So answer for v will not change, but answer for u changed, right? U no longer has v. Then we will just take v and we will connect it to u like this. And this will update v's answer. So the way we are going to do this is, so let's just take a look at how this will update. So when we detach v, so step one, detach v. That means dpup will be equals to the sum over, let's use a different, let's use w. W belongs to subtree of u, t to the power p of u to w minus all the nodes that are in the subtree of v are now gone. W, let's use z. Z belongs to subtree of v. dp uh, v to, okay, yeah. So notice that when we are removing u, I mean when we are removing v from u, the answers that are in u have one extra edge compared to the answers for v, right? Just like we had it before. So what we'll have again is that we'll have d to the power, no, we'll have d of v to w plus 1 to the power p. These need to be subtracted. So then again we can use binomial expansion here, right? We will do um, z belongs to subtree of v, uh, then sum over j equals 0 to p, pj, then d to the power j, v to w. Now this thing can be written as the w that belongs to subtree of u, but do not belong to the subtree of v. Those ones, and we will have the ones that belong to subtree of v, right? So uh, okay, we can't really separate these two because we don't know how they separate out. But yeah, so this thing is dp currently, and from that we will subtract this thing, and this thing we can write just as we did before. We will swap the summations, right? We will swap these two summations, and then we will get an expression of this form. So we will get that dp uh, equals dp minus sum over j equals 0 to p of pj dp vj. So this is how u is updated. So first we updated the value of u. Now what we need to do is connect v. So when we connect v, what happens? We have the answer for v, that is dp, vp, whatever. And then this value for new value for u we have, let's call this dp up prime. Okay. So we have right now dp up prime here, right? So how do we do that? We'll get dp vp, let's say prime, is equals to whatever answers were here will not change. So we have dp vp plus we need to add the answers from here, right? The answers from here would be um, again we are going to have some w belong to the new subtree of u, which we already calculated here. So that d u w plus 1 to the power p. So this needs to be added. Again, the plus 1 is because we have this extra edge over here. So again, you can do binomial expansion and you will get basically sum over j equals, I just skipped a step here, pj, and then dp prime uj. And this is how this we will update. So now that you found the answer originally for UP, then you found the answer for you found the answer for VP, because now the answers are for V as the root, right? So like this, you can basically do DFS, right? Because every time we are going into a child, so what we are basically doing is we are taking our tree, we are moving it over. If we are going to here, we'll just change it like this. And then if you're going here, we will change it like this. Then we will go back in our DFS. So then it will again become like this. Uh, ah. So every time you do this, you are going to call a function reroute u to v, which will perform these two steps for you. Step one, step two, which is remove u, connect v. So like this, you can calculate the answers for all nodes. and then you can sum up for answer, right? So let's see what the time complexity of calling reroute is. So you will be making p steps, right? This is O of p because you're summing over p. So basically, yeah, this one is NP. The time complexity for this is NP. So then basically you will just have O of NP into P. That is O of NP square. And this one will pass because P is less than equals to 10. And that's how you solve this problem. So we have used rerouting DP. Okay. Any questions you can post in the chat. Um, okay, if there are no questions, I'll move on to G. So G is a fairly difficult problem. Uh, what the problem is that you are given a grid, right? Let's say it looks something like this. So this grid always has four rows, right? One, two, three, four, and you need to find the number of ways to step one, pick a tile. You pick a tile in the grid, and step two is that you make a closed loop. For example, like this. Step two, make closed loop. And obviously, the closed loop must contain your initial point. The topics you will need to solve this question, at least the way I did it, are DP, matrix X, expo DP, and matrix geometric series. So at first sight, you see that n is less than equals to 10 to the power 18. That probably I mean you might think that that means there is some nice formula that you can use, right? Uh, but I don't think a formula exists that's easy. Instead, you will have to do it with DP and then you will have to speed it up with matrix exponentiation. So, first of all, how do you do this with DP? Let's say that you already have the answer for, by the way, this is n. This is n, the number of columns. Uh, yeah, so for n, let's say you have the answer for n, and now I will add in one more row. Okay, let's say n minus 1. Now you add one more row to get the answer for n. So the question is, how do you get answer for n from answer of n minus 1, n minus 2, and so on? Uh, there are a few smart ways of doing this problem, which uh, one of them I don't get, and another one is basically by using some interpolation techniques. But the way I did it is to painstakingly figure out all the patterns that are possible. So what we will do is that um, draw all possible patterns of paths. By the way, notice that basically this two-step process, let's say you only wanted to only count number of paths, number of closed loops, right? So that is some value, right? Now let's say you have some closed loop that has length L, and in this problem, this loop would count as just one, right? But if you were counting this plus number of ways to start at a point, number of ways to start at point on loop, then that is not just one, right? There are L points on this loop, like this, L points. And you could have started anywhere. So that means in this problem, this one path counts as L, right? Which means it's a bit of a problem because you have to now calculate, you have to factor in this L while making your calculations. So the procedure is to basically, let's say you had a path, right? You had some path, and then you extend this path a little bit. If you are going by patterns of paths, let's say this path was pattern A, but after adding the small loop, it becomes pattern B. So basically, it's like your answer, BP, let's say B, comma for n, is equals to the number of possible paths of pattern A that you could have had on n minus 1 plus plus you added some edges, right? Some edges were added. So let's say you added k edges plus k times the number of paths you can form of pattern B. So that's like, um, no, sorry, not. The way I said it was after adding this, it became of type B. So how many ways can you form a path of type B? Something like that. This is a different DP. This is the number of paths. And this is our original problem. So, well, the types of, basically, let's just say that our path on the last row ends in a couple of different ways. You can have, you can either, you can not visit these two and you can visit these two, or you can have something like this, or you can have something like this. This is visit, not uh, not visit, and there is another type which I'll come to in a bit. So then you could have like this, and you could have like this, and you can also have things like this. So what is this? This basically means you came here and went back. One example of this path would be something like this, for example. Here you see, if you take just the last row, you visited both these points and you went and came back here. So if you draw all the paths of this type, you will have something like this, uh, and then something like this. Now notice that some of these are symmetric, in the sense that this and let's call it A, B, C, D, E, F, G, H. So A and E are the same if you flip them on by if you reflect them, right? This one, if you reflect, then you will have uh, E, right? So what this basically means is that we just have to add a 2 whenever we see A, like multiply A by 2 and forget about E. So this way we can remove E, we can remove D because D is same as B, and we can remove H, which is same as F, right? So now we have these different types. Oh, we have one more. We have this one. We have uh, this this type. Uh, so now basically you have what A, B, C. So let's just draw out all the valid paths. So it's 2 into this plus 2 into uh, this plus uh, C type plus D type, this type plus this type plus this type. So we'll call this A, B, C, D, E, F. So we have 6 types of patterns. And basically, the whole problem is that you need to figure out how you can basically connect these. So the way you can do it is you assume you start here. So this is say A n minus 1. Then how can you go to the next row? So one way is you just directly go like this. Then you have an, right? Or you could go like we can go here and then go here and then you go here. So that means we have bn, and then you can go like this, or you can go like you can't go like this. Yeah. So this is cn, right? Because you have something like this. So find all relations, and what you will have is coupled linear recurrences. So I'll write down what the equations are. So you have just a moment. Uh, yeah, no, wait. Give me. Yes. You have these equations basically. You have a n is equals to a n minus 1 plus b n minus 1 plus c n minus 1 plus e n minus 1 plus 1, because if you have 2 rows then you can form something like this, a box. And then you will have bn en minus 1 plus cn minus 1 plus uh, 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 plus 2bn minus 1 plus bn minus 1 plus 1, and so on. Like this you will have a whole bunch of equations up to fn. So now that you have these, that just solves number of paths, right? But then you also have to consider the number of ways you can pick a point. So for that, basically it just means that, as I said before, say I went, let's take this example. I went here and then here, like this. and then I ended up at uh, B type, right? So what that means is that I had these have to be closed loops, right? So let's imagine there was an edge here, and let's imagine there is two edges here to close the loop. Now, basically, you have to see that your path turned from A type to B type, and how many edges were added, how many uh, added. So how many were added is this was removed and these two were added. So one, these were also added. So you have 1, 2, 3, 4, 5, 5 minus 1 for this one equals 4. So let's say by an, bn, dot 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 up to fn, that's the answer to this problem. So you have an is equals, no, sorry, bn is equals to bn minus 1. No. Something like this. An equals bn plus 4 times uh, bn minus 1. You'll have something like this basically. Oops, I switched those. An plus 4 an, right. So the number of so the answer for bn is equals to an, which is this whole section over here, plus the number of paths of a type. So you're adding edges, add edges to a type paths. So that means you added 4 edges, so you have plus 4 times an minus 1. So like this, you will get a lot of relations and you will get these equations. You will get something like an minus 1 plus 2 an minus 1 plus bn minus 1 plus 2 bn minus 1 dot 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 up to fn. So now these are coupled equations, coupled between uh, a to f and small a to small f. So that means you basically have a set of 12 equations, right? So now these 12 equations you can solve with dp. Solve with dp. So it's a 12-dimensional dp. But this is still not good enough. Why? Because you can only solve it in O of n time, which is not good enough because n is less than equals to 10 to the power 18. So how do we solve this? The way to solve this is something called matrix exponentiation. Now what is this? What do I mean by that? What I mean by that is that let's take a simple example, right? Let's take Fibonacci numbers. So what's the recursion for Fibonacci? It's Fn is equals to Fn minus 1 plus Fn minus 2. Now notice that we can write this as a matrix equation. So what we'll write is that, so Fn minus 1 is equal to Fn plus 1 Fn. So we'll make this transformation. Okay. Oh, actually Fn minus 2 Fn, uh, just a moment, messing up the indices. Yeah, right. So if you want to get this, so how do you get Fn plus 1 from Fn and Fn minus 1? So Fn plus 1 is equals to Fn plus Fn minus 1, right? So that means you put down 1 1 here. So if you do matrix multiplication, you will get Fn is equals to 1 times Fn plus 1 times Fn minus 1. And then you can just see that Fn and Fn are here, so you can just put 1 0. So 1 times Fn plus 0 times Fn minus 1 is Fn. Makes sense, right? So you can write this again for Fn minus 1. You can write is equals to Fn minus 1 Fn minus 2 1 1 1 0. So if you keep doing this, in the end, what you'll get is that Fn plus 1 Fn is equals to the matrix power of to the power n of your initial values f0 and f1, which are equals to which are this is equals to 1 1, right, or 0 1 depending on your convention. So basically, to get the solution up to n is equals to matrix power of this multiplied by a vector of initial conditions. So let's say this matrix is something m, and we want to calculate m to the power n. So solution is matrix exponentiation. Now, how do you do usual binary exponentiation, right? So let's say we want ak is a to the power k. How do you do it? You do if so f ak is equals to, if k is even, then you just call f a square k by 2, right? And if k is odd, then you do a times f of a square uh, k minus 1 by 2, right? So uh, so that means like you can calculate this easily, and this works in O of log time, log k. Now you can do the same thing with matrix expo, just change a to m and k remains k. So this is going to be exactly the same, that fmk is equals to f m square k by 2 if k even, and otherwise it's m times f m square k minus 1 by 2. So this works in O of matrix multiplication. If m is n cross n, matrix multiplication is O of n cube. So you'll perform a multiplication log k times. So O of n cube into log k is your answer. Now note that the way we defined our answers before, I should have made this clear earlier, but an or small an or capital An are answers for paths uh, ending in nth row. So, what is the answer, by the way, up to the nth row? Like for the nth row, for paths ending in nth row, what is the total answer? So, as we said earlier, A should be multiplied by 2, B should be multiplied by 2, since they are reflected. So, we'll have 2 times An, since we are summing over all possible patterns of paths that are possible. So 2an plus 2bn plus, if we go up and look at our path patterns, so we'll only count the path pattern, only count pattern if we can close the loop. Note that that means like f You cannot close loop. You cannot close loop because there is no way to connect this and this point in the same row. So F we will not count, but E we can close like this, D we can close, C we can close, B we can close, A we can close. So we have 2 times A, 2 times B, C, D, and E. So the answer is the total answer is 2AN plus 2BN plus CN plus DN plus EN. So now we want sum over Tn from 0 to n, right? So how are you going to do that? So what does this basically mean? We have some we have our initial conditions. We have initial conditions, and we are going to have m to the power 0, then m to the power 1, then m to the power 2, and we'll sum up all of these, right? So we have m to the power 0 plus m to the power 1 plus m to the power 2 plus dot 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 up to m to the power n minus 1, I guess. Yeah. So this is nothing but a geometric series. But the question is how to calculate quickly. You might think that you can do m to the power n minus I over m minus I. Oh yeah, for those who are asking which problem we are at, we are on problem G. We are on problem G. Yeah, so you might think you can do this, but this is not always true because you would have to invert this matrix and you don't know if it can be inverted. So the way we are going to solve this problem is that we will again use something similar to binary exponentiation, matrix exponentiation. So what you do is that uh, if k is even, so let's say k is equals to 2 L, right? So you have 1 plus m square dot 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 up to m to the power 2L. So you take out 1 plus m square up to m to the power uh, L minus 1. You take that and you take m to the power L common from the remaining part, 1 plus dot 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 up to L minus 1, and then you take m to the power 2L separately. So if we define f of mk is equals to 1 plus m square up to uh, m to the power k, then f of mk is equals to uh, 1. So we can take this common and we can write it as 1 plus m to the power l minus 1 into 1 plus dot 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 up to m to the power, no, 1 plus m to the power l into 1 plus m to the power n minus 1 up to that plus m to the power 2l. So that is 1 plus m to the power l times f of m to the power k by 2 followed by m k by 2 minus 1 plus m to the power k if k is even, and if k is odd, then basically you won't have this 2 to the power L factor. So if k is equals to 2L minus 1, then you can just write it as like this. M to the power 2L factor won't be there, right? If k is equals to 2L minus 1. So if k is odd, then the answer is like 1 plus m to the power L, 1 plus m to the power L minus 1. So that's 1 plus m to the power k plus 1 by 2 times f m uh, k minus 1 by 2 if k is odd. And note that k is being at least halved in every step. So your time complexity will be something like O of n cube log k square probably. I'm not entirely sure because you are performing matrix expo in every step. So you'll have something like this for matrix geometric series. So that means you can solve this problem in. So you had 12 equations, right? So you'll have a 12 cross. You might think you'll have a 12 cross 12 matrix, but if you have a constant in your equation, like say I had fn minus 1 plus fn minus 2 plus uh, some constant like 6, then you would have a 3 cross 3 matrix. You would have 0 0 1 uh, 0. So you would write fn minus 1, fn minus 2, 1. And your fn is, so this is equals to fn minus 1, 1. So fn is equals to 1, 1, 6 because fn minus 1, 1 times fn minus 1 times fn minus 2 plus 1 times 6, which is 6. And then this is same as always. So you'll have a 3 cross 3 matrix. So because of constant term, which we had in the equation for A, if you recall, here we had a constant term. We'll have constant terms for capital A, B, C also. You'll have a 13 cross 13 matrix. So it will be something like O of 13 cube blocks square 10 to the power 18. And this will pass. And that's how you get the answer. So we have used matrix geometric series here. I didn't write down the full equations because if I write them down properly, it's going to take like more than half a page. But basically, once you have found out those equations, you just have to copy them into the code and you have to do matrix export. But it's pretty hard to do it. Any questions? All right. Um, okay, so let's just look at H. So H basically the what you really need the most is something called linear basis. And this is there is a Codeforces blog on it, blog by Errorgorn. So just take the code from there or read and understand this blog. Once you understand this blog, you will get an idea of how to solve the problem. I mean, not right away, but I will explain how to solve the problem provided you know how to do linear basis. Uh, so basically, the problem is that you are. Just a moment, where did my cursor go? Oh, there we go. Uh, oops. Give me a moment, please. I think my shoot. There we go. Yeah. Yeah. So basically, what our problem was that we are given some set S which contains some numbers in base k, right? So you take a number, say, for example, in base 2, if I write 13, it's going to be 1101. And then if I want to write 5, it's going to be 101. And you have a machine which takes two numbers and takes their bitwise, I mean, not bitwise, takes their digit wise sum modulo base modulo k, right? So for example, in base 2, if I wanted to do 1101 plus 101, you would get 1202, but we are doing modulo, so this becomes 0. So you will have 1000, which is 8. So uh, now the problem is that, one, you add a number to your set. Two, given a number x in base 10, but you can convert it to base case. So let's just leave that out for removing confusion. Given x, you want to the find number. So so basically, we have a definition of good numbers. Good number is take considering the numbers in set S. Considering the numbers in set S, can you have a linear combination? So can you have a linear combination of numbers in S, A1, S1 plus uh, uh, plus A2, S2, which is so if X is a good number, that means considering set S, you can have a linear combination of this, which is equals to X, where the plus is basically your digit wise uh, digit wise some modulo k. So now, yeah, you need to find the number of good numbers which are less than equals to x, and 3 was given x, you need to find x's smallest good number. Now, so if you know linear basis just maintains. So basically, what are these? These are vectors, right? Vectors of length of length uh, some length d. So like 13 is a vector that looks like this. 5 is a vector that looks like this. And basically, we are doing these additions modulo k, and there is a name for that. We call it z over kz, which is integers modulo k, and you have some d of those. So basically, it's like z by kz cross z by times z by kz. So you'll have z by kz to the power of d. And in this notation, like basically, we are maintaining a basis set. So basis set means you. All good numbers uh, are a linear combination of basis vectors. So if you know linear basis, adding this is trivial. It's given in the block. I mean, it's not trivial, but it's in the block, so you can look it up. So you may think that solving 2 and 3 are hard, like solving both of them, but the good thing is if you solve 3, you also solve if you solve 3, then also solved you have also solved 2. And if you have solved 2, then you have also solved 3. And why is that? I'll give why this one is true. That's because you can just do binary search, right? So you guess a number, you find the mth smallest good number, and you check if less than equals to x. Uh, if it's less than equals to x, then you do L equals mid plus 1 and set answer equals to mid. Or if it's greater than, then you set r equals mid minus 1, and this way you can do binary search. Which means we only need to solve 3. Similarly, you can prove this one also. So you only need to solve 2. So basically, only need to solve one problem, right? So the question is, which one is the easier problem? So as it turns out, the easier problem is number 3, which is to find the exact smallest good number. And well, to proceed forward, you really need a strong understanding of linear basis. So, which I don't know if anyone in this audience has, but I will just give an idea of how it works. It's basically like you try to fix each digit. So you go from left to right, and you see uh, what. So your basis basically looks like this: some values 0, some values 0 0, some values. So basically, once you fix this, this is also fixed. Like this is already fixed. Once you fix this, this is also fixed. Once you fix this, this is also fixed. So basically, you only need to check diagonal diagonal elements. So there are some equations, and you just uh, do for loop uh, over diagonal elements, and you solve that equation at each step. Solve, and once you solve and add up, you will get your answer. I realize this is not a very clear explanation of what's going on, but I mean, it's going to take solid understanding of linear basis to understand what equations I'm talking about. But trust me, they are very simple equations, and that gives you a solution for 3. And once you have solved 3, you have also solved 2. So yeah, that's it for each, I guess. If you want to see the solution, I guess we will open submissions sometime, and then you can see those. Yeah. Any questions? I mean, is there anyone who wants me to go over the solution for H properly? I mean, okay, I guess not. Then we are done here. Um, hmm. Okay, okay. Yeah, I'm done. Shubham, are you there?
Yes, so it was a nice discussion session. So now Subham
Yeah,
will take on CD. So thanks a lot, man.
yeah.
Okay. Subham, are you there? We'll take 5 minutes break, kind of, then, or 2 minutes. Subham, can you try screen sharing?
Am I audible?
You are audible.
Okay, let's start. Um, I think the screen will be visible. Can anyone confirm if the screen is visible or not?
It's visible right now, so we can continue, I think.
Okay. So hello guys, my name is Shubham Prakash and I will be discussing problem C and problem D of yesterday's contest. So let's start with problem C. Okay. Okay. So in the problem, we are given an array A with n integers and we are also given a number k. Okay. So let's say we have some elements a1, a2, and we have two players. Uh, let's call them x and y, and each player have each player can make any one of these two moves in each turn. Either they can select a number ai such that ai is less than equals to k, and then they can add x, remove I, and add ai to their points, and or they can select if ai is greater than k, then they have to select a number. Then basically they have to break that number ai into two parts. It could be 1 comma ai minus 1, 2 comma ai minus 2, and so on. And yeah, you can't break those numbers into 0 and ai because it's still the same, right? And then you need to place those numbers, and then you need to insert those numbers back into that array. Okay. So the goal is the x player x is starts first, and the goal of the players is to maximize their points. Okay. So say player x starts first, and both of the players will try to maximize their points. That's the problem. And the constraints for the problem are n was up to 100 it is, and ai and k were up to 1. Okay. So, so that is the whole problem. So let's So let's jump into some observations. Say we sort the array, because we can obviously, the ordering does not matter, right? So if we sort the array, then we will have some numbers from A1 to AN. And let's say the player X have to make a move. Uh, if there is any number, if there exists any number ai which is less than equals to k, then player X will obviously try to pick ai, right? Because taking doing the second kind of operation when you have a number already less than equal to k is not a good option. Is that clear? I mean, if you have already numbers which are less than equal to k, then doing the second operations will just improve the state of the game for the other player. So if there is any number less than equal to k, then player X can pick that number. So, and among those numbers it is best to pick the maximum number, because we will make that greedy choice to maximize our points. So if we break our initial array to, let's say, two sets, one contains some AI1, AI2, and up to some AIP. It contains some of those numbers, and all of these numbers are less than equals to k. And we have another set which contains the remaining numbers. Let's say the remaining. We will talk about this other set later. But first of all, in this particular set, uh, we will make the greedy choice of picking the highest number, and each player will do the same thing. So basically, uh, player X, if we sort the array and let's say we find the last index where ai is less than equals to k. So if we have a1, a2, a3 up to ai, then we will pick ai, and the second player will pick ai minus 1, and so x would be ai plus ai minus 2, because ai minus 1 is picked by the other player, and so on. Same goes for y. He will also take alternate turns and pick ai minus 1 in its first turn, and so on. Thereafter, all we have left is these remaining numbers. So these numbers are greater than k. Okay, and one of the, and what is the, like, let's say we have a number. Let's take a sample example. Let's say our numbers are 1, 2, 3, 1, 2, 3, 4, 5, and let's say 6 also. And we are given k equal to, let's say, 10 for now. Then we can, all the numbers are already less than 10, so we can obviously make the greedy choice, and in this case X will have this 6, this 4, and this 2, so the total would be 12. But what if the k was, let's say, 3? Okay, then X will definitely pick 3 and 4 in its turn, 3 and 1 in its turn, sorry, and Y will pick 2. So the total all we have left is 4, 5, 6. So in this scenario, let's say we also have some more numbers, 7, 8. Okay. So what is the best move? Let's say a player X have to make a move in this turn, and he has 4, 5, 6, 7, 8 in the array, and K is 3. If he picks 4, then no matter how he disintegrate the 4, he will end up with a number which can be picked by 1. If he convert a 4 to 1 and 3, then y can pick 3. If we convert 4 to 2 and 2, then y can pick 2. And yeah, so it's not a good option to give to give away y some points. But even if you pick 5 or 6, the same thing still applies, right? Let's say he picks 6, then If he even break it into 1 5 2 4 or any other possible combination, then y can take up one of the numbers and the other number is still in the set. So we don't want that, right? So here the best move for x would be to pick 7 or 8. Let's say he picks 7, then he can break it into any way he wants as long as both numbers are still greater than 3. So let's say he break 4 into okay, let's not take 4, let's take 8, because for 7 again, if you break 7 into any two parts, then one of the numbers would be less than equal to 3. If we take 8, then we can break that into 4 and 4. Then we didn't really give y a choice to pick a number. So when the turn of y comes, y will have to pick a number, and the remaining numbers are 4, 4, 4, 5, 6, 7. Now, if y makes a move, then in next move, x can surely take a number, right? So, wha- in if I generalize what did I just said, so I have a number k, and there are some number a1, a2, up to ai. Let's say they are less than equals to k. Then we can make alternate moves to by picking the highest one first to get some points. And then we have number, let's say ai plus 1, ai plus 2, up to aj. And if and they are up to 2k plus 1, they are less than equals to 2k plus 1, they are less than equals to 2. Why 2k plus 1? Because if I have a number 2k plus 2, then I can still break that into k plus 1 and k plus 1, right? And this moves, after making this move, both of these numbers still are greater than k, right? So if I have some more numbers, let's say aj plus 1, aj plus 2, and up to an, then I can pick any number and break into two halves so that both are greater than k. So first of all, we make a greedy choice in this area, and we will have some updated x and some updated y. And then we will make operations on these numbers, because making we can make operations on these numbers such that all numbers are converted to some of these numbers, which are less than equal to 2k plus 1. So for the given example, let's say we pick 1 2 3 greedily. We picked 1 2 3 greedily, right? And afterwards we had 4 5 6 7 8. So we had 4 5 6 7 8. So in the next move, I will surely make it 4 4 4 5 6 7. Yeah, 8 is no over there. And then the other player, wa- now the other player has a choice. Sorry, the other player, the player who have to play the current move does not really have a choice. No matter which number he picks, he will have to split it into two parts, in which one part will be taken by the x or the opponent. So will he pick? Is it good to pick 5 or any odd number? If he picks 5, uh, he can split it into 1 4 or 2 3. Yeah. But in both these scenario, the other player can take 1 in this, and he will take 3 in this example. So at first glance, it seems that splitting in 1 4 is better, because we are only giving away 1 point to opponent. But the problem in this scenario is 4 is not actually picked by us in the next move. 4 will go back to this set, and I will again have to make a split in which the opponent will get benefited. So basically, whenever we end up in such situation in which we will have to make a split in which the other opponent can take one of the integers in his next move, we will split the number into two halves. So in this example, I will make the split of 2 and 3. If I split into 2 and 3, then the opponent can pick 2, but in the another move, we can pick 2. Okay, sorry, opponent will pick 3, and we can put 2 in my next turn. So, but we are still giving away one extra point to opponent, right? Because it's a odd number, so opponent can get one number more than me. So I will pick an even number in this scenario. So basically, in this example, I can pick 4 or 6. If I pick 4, then my array would become 2, 2, 2, 4, 4, 5, 6, 7. Now the opponent will pick 2, and I will also pick 2 in my next turn. Now the opponent is given this set. Now he will again make a greedy choice of picking 4, and in this way, at each move, if I pick a odd number, if I pick an odd number, let's say m, then I will get m by 2 floor, but opponent will get m by 2 plus 1. This is the case when m is odd. But if m is even, then both of us will get m by 2 and m by 2. So in this scenario, so picking the even number is obviously beneficial. So uh, that's what we will do. Where the both me and the opponent will keep on picking even number as long as there is a even number in the array. And when all the even numbers are exhausted, then we will start picking up odd numbers. And first of all, if there's any number which is greater than 2k plus 1, then we can pick that number and split it, right? And in this way, all we are left is numbers in this range from k to 2k plus 1. And in this range, then we can pick all the even numbers first, and then we will pick all the odd numbers. So, and at the end, for all the numbers in this range, if they are odd, if any number, if I pick any number in this range m, then if I make the choice of picking it, then I will surely get m by 2 floor, and opponent will surely get m plus 1 by 2, which is this is basically, or I can say that seal. Okay, so first we will make greedy operations for all numbers less than equal to k. Then we will make greedy operations on this, in which we will pick the even number first, and then for odd numbers we will pick the highest number first. And the ordering actually doesn't matter, because anyways we are for any number m we will still get half, right? So doesn't matter if m is even, then it doesn't matter whether opponent picks it or I pick it, I will still get m by 2. But if it is odd, then I will get 1 less than opponent. So first I will try to pick even number, and then I will try to pick the remaining odd numbers. So that's the whole algo. You will basically for and now you can, for checking the odd numbers, you can just find the number of. So basically uh, we for this part, let's say we have updated the answer. So we have some ai for all ai. Okay, not this. A1, A2 up to AI, where all of the numbers are less than equal to k. Then we have some AI plus 1 up to an. So the points of x would be ai plus ai minus 2 up to, it can end with either a2 or a1. I mean, it depends upon parity of I. And then uh, I can count number of odd from ai plus 1 to an, and I will simply add ai plus 1 by 2 floor plus ai plus 2 floor up to an plus an by 2 floor. And if there are, it depend, we will first check that after making all these operations, after making these moves and these moves, whose turn is it? I mean, if it is X turn, then X is at a loss of some points. If it is X turns, then X will get C by 2 floor. Okay. If after making these operations, it is X's turn, then we will have X plus equal to C by 2 floor, or else X will get C by 2 C if it is Y, if it is the turn of player Y. So that's the final solution we have. First, we will perform these, and then okay, let me use yeah. So first we will perform this. Then we will check how many numbers of odd are there in the range AI plus 1 to AN. What is AI plus 1? AI plus 1 is basically the first number which is greater than k, and this array is sorted. And then X is basically sum of floor of all AI from which are greater than k. And then we simply add C by 2 floor if it is X's turn after making all these moves. So that's all for problem C. Does anyone have any doubt? Okay, it seems like it's okay for everyone. So, do you want me to show the code of this problem, or we can move to problem D? Okay, let's move on to problem D then. Okay, so in problem D, we have an array A of length n. Let's say it is A1, A2, up, up to AN. And we also have a pile of stones in which there are n stones in the beginning. Okay, we have n stones and we have a array A where n is less than, I guess it was 2000, 2000, and AI is less than n. Okay, so and we have to make some moves, so that we have to basically remove stones from the piles to make it empty. And we have to find the number of different sequence of moves we can make. So let me first define what kind of moves I can make. First of all, in very initially, I will pick any index I, ith index, and then I will choose some number r such that r is greater than ai. Wait. We'll pick a number r such that r is greater than ai, but it should be less than equals to j. What is j? j is j is number of stones in pile. Number of stones, the current number of stones. Initially j is equals to n because it is r stones from the pile. So if we had j stones, we will remove r stones to make it j minus r. That particular sequence, and then okay, that particular move is defined as I comma r. basically I1 comma R1. So the first moves in which we first have the index, and then we have the uh, number of stones we remove in on that at that particular move. Okay, and after making this move, I can change my ith index to any particular index k such that I minus k mod is less than equals to ai. So basically, I can move to I can move to index k such that it it lies in the range ai minus I minus ai, and it could be in range I plus ai. And obviously we will have to make sure that this is not negative and this is also less than n. But as long as it lies in that range, we can move to a index k. So what did we do? We made a move. We removed some r stones to make the number of stones j minus r, and then we moved to some other index k. And the sequence is formed as, let's say you in the first move you pick the index I1, you removed R1 stones, and then you move to index I2, and then you pick R2 stones, and so on and so forth. After some m number of moves, let's say after these many moves j becomes 0, then this is one of the sequence we have. And we have to find number of such sequences. This is called a winning sequence, and we have to find number of such sequence modulo 1e9 plus 7. So how are we gonna proceed in this problem? So in this problem, we will use a dynamic programming approach. Okay, we define dp ij as number of sequences if if we start with I, ith index, and j stones are remaining. J stones are remaining. So how can you find dpij? Basically, we can remove some r number of stones, right? And must be r must be greater than equal to, sorry, r must be greater than equals to ai and less than equals to j. So, and we can move on to some k index where k is less than equals to I plus ai and greater than I minus ai. So dpij would be, summation. If I remove r stones, then basically I will have x equal to I minus ai to I plus ai, and y would be in the range. The remaining stones could be at least 0, or let's say at least 1, and it could be at most j minus ai. Okay, let me make it clear. J equals to okay, x equals to I minus ai to I plus ai, and then we have another summation in which we have y equals to 1 to y equals to j minus ai, and we need summation of dp x comma y. And we also add, because we can obviously make a move of I comma j in every term. We can remove all the stones we had. So that's one sequence, and the other possibilities are covered by this. Okay, so if you go by this approach, then first you will have to calculate on the index of the array. Making O of, and we have a complexity for transition for dpij, and you need to calculate dpij for the entire matrix. So we'll have O of n to the power 4 solution. But it's still correct, right? It is correct, but the complexity is will not fit in our limits. So what can we do to improve it? To compute this number, we need to have the sum of the values of the rectangle enclosed by these two lines. So basically, let's say let's say this is I plus ai, and this is, okay, let me make it a bit clear. uh, plus ai, and this is I plus ai row, and this is some ith row, and we need to compute dp I comma j. For computing this, basically, and j minus ai. So this column of j minus I enclosed by this. This is the rectangle, and we know between y equal to 1 to j minus ai, and x is between I minus ai to I plus ai. So we will compute dp in this direction. First, we will compute it for the first row, and then we will go to second row. And for the jth row, when we are computing dp I comma j, then all the values in to the right of it are filled already, right? And we can find the sum of this rectangle in O of 1 by using prefix sum. If I make a prefix 2D array, if I make a prefix 2D array, then I can easily get the sum of this rectangle in O of 1, right? So whenever we are calculating dp I comma j, we will also update prefix I comma j. And how do we make prefix 2D array? Basically, pf ij is nothing but dp I j plus pf I minus 1 comma j plus pf I minus 2 comma j. I comma j minus 1 and minus pf I minus 1 j minus 1. You'll need to consider the boundary cases when I is 0 and this will become negative. But other than that, first we will compute dpij, then we will update dfij. And yeah, the updation of dpij is given by dpij would just be sum of the sum of x1 comma y1 and x2 comma y2. Basically, sum of the rectangle enclosed by x1 y1 and x2 y2. What is x1? X1 is basically I minus ai. X2 is basically I plus ai. And y1 was 1 and y2 was j minus ai. So after finding this sum, we will update the prefix sum also. And in this way, at any point of time, if we are computing dp I comma j, then we have the information of everything on the left side of the matrix, uh, and that's how you can easily compute dp ij in O of 1. And since we have to compute it for each and every cell, so it will take order of n square, right? Because the maximum value of j could be n, and the number of rows was obviously n. So we will have the order of n square solution. So dpij is basically sum of this plus 1, because we didn't include the case where I take all the numbers at the ith index. So after making this update, we will also update pfij. Is it clear? Does anyone have any kind of doubt? For this one, should I show the code or is it okay? Once you see the application of prefix sum in this problem, it's not very difficult. First, you have to think that what is the definition of dp, and then you can easily come up with the transition that it's the sum over all these values, and plus 1 for the sequence I comma j. And we saw that we can't computing this sum in order of n square will give us a order of n to the power 4 solution. So that's why we use prefix 2d array to do this transition in O of 1. And we will have to update dpij and pfij at every instance, and at the end you can make order of 1 transition, which will lead your overall time complexity to become order of n square. Okay, so I guess that was all for this problem, and like that we covered problem C and problem D, and
Yeah, so
I will ask Ayush.
right. So it was nice discussion by you. Okay, so now we can continue. First of all, let's thanks both of them, Manak and Swam. They found time and they discussed still all the problems like CD and FG and H. So we can now begin A, B, and E. I'll be taking this. So okay, I can continue this.
Okay, thank you, Ayush.
Uh, is my screen visible? Can someone comment? Currently, no one is in StreamYard, so any of you will have to comment in the comment section. Okay, okay, cool. So we can start A. A is a no problem. Like it's just basically, see, there will be three cases. First will be C less than, since we know A is less than equal to B less than equal to R and greater than equal to L. So first case will be C less than equal to A. So in that case, sorry, I'm using the first time iPad basically, so it's weird. It's A minus C plus B minus C. So it will be equivalent to A minus C plus B minus C, which is equivalent to A plus B minus 2C. There will be second case where C is greater than B but less than A. In that case, you can open the mod as just A minus C plus C minus B, which will be equal to B minus A basically. So this is a constant, right? Now we have the third case, which is C is greater than equal to B. So in this case, it will be C plus minus A plus C minus B, which will be equal to 2C minus A minus B. So you have to basically maximize the value of mod of A minus C plus mod of B minus C. So what can you take the value of C basically in both of them? This is the constant. So here if you take C is equal to L, here if you take C is equal to R. So how do we change the, okay, I think from here, okay, right. So the answer should be max of A minus L, basically A plus B minus 2L, comma, 2R minus A minus B. Basically I replaced R with basically I replace C with L and R. That's all A. I mean, is there anything doubt in A? I think there won't be, right? So we can jump to B, right? कुछ तो बोलो यार. Okay, I'm going to B. So this was a very nice problem. Basically, Pritesh had done it. I'll be so let's begin the discussion. Okay. So what you do in this problem? You just the only thing you have to take is if j is equal to 2 to the power k, then it represents a binary number with only kth bit set, right? So you have to just loop through. Wait, oh my pen. Hold a minute. Okay, so see. So we will claim something. So we will claim that only you have to check j is equal to 2 to the power k form. Okay. So I will prove both of them. Like there is a trivial, right? A XOR I is equal to. Basically, this is the thing we need, and we know this. This is trivial, right? Isn't? Okay. So we'll take j as a form of 2 to the power k1 XOR of 2 to the power k2. This 2 to the power kn. Okay. Now I will start with LHS. I will go to RHS. I will just go through the proof. We can see the code later on after I complete the proof. So basically, A I XOR of j is equal to A I. I'm keeping this 2 to the power kn outside. That doesn't make any difference. So it's fine. We can write it in this form, right? Isn't? We just saw above from the trivial case. We can write it in this form, and from there we can go to here. Okay, this is fine. Is screen not visible? Is screen not visible? Uh, oh wait, what did just happen? Okay, now is it? My iPad is disconnected, I think. Okay, fine. Okay, right. It's okay now. Okay, great. So where was I? I was there with we are proving. Okay, so AI XOR till here I had done right. So we can complete it here. Wait, I will just take a new page. This is clear. That will be equivalent to this. So it proves from where we begin with. Okay. So ultimately, we proved it that, like, see, we basically started with LHS, we are coming to RHS, right? So, okay, you are asked, can you please explain the theory again a little bit? Okay, right. So basically, we did take a trivial case, AI XOR of A to the power 2k. A basically A 2k, okay. So that will be equivalent to this. How do you back to the page? I think from here. How do you go back to the page? Back page or something? Okay, right, this way. Okay, all right. So we took this trivial case, okay? Hmm. We took this trivial case, right? So from here, I mean, this is clear. I mean, I need not explain AI XOR of 2k is equal to. So here I am taking j is equal to 2 to the power k1 XOR of this whole number. So I'm basically taking XORing any index I with 2 to the power k, because effectively it will just flip the kth bit of I, right? For example, if you take j is equal to, if you take j is equal to 2 to the power k, then it represents a binary number, right? So with only kth bit set, like all other number bit are zero, only kth bit is one. So for example, 2 to the power 0 is equal to 1. So it's in binary it is 0, 0, 1. 2 to the power 1 is equal to 2, in binary it is 0, 0, 1, 0 basically. So just kth bit is set. Other basically others are basically 0 and just okay, right. So every index j can be represented as a combination of XOR operations with different 2 to the power k value. Checking just j is equal to k, I think should be enough, right? That's what I'm trying to make you all understand. So I begin with taking j is equal to 2 to the power k1 XOR all this, and I started with LHS, and I ended up with again and to the RHS. So this is what the proof is. You can uh, pause and like rewatch the video if you want to see the proof again. I have to go to E actually. So I'll once show the code also. I mean, code should be simple enough. So, see, this is the same thing I'm doing here. I'm taking k is equal to 2 to the power I form and then doing again the same. Okay. What I made try to make you all understand. If it's not equal, I'm taking it as a no, otherwise yes. Okay, fine. TLE, okay. Actually, earlier we had kept it as 2 to the power 64 max limit constant. We decreased it to 2 to the power 60, I think. That should not give TLE basically. So wait, let me go to E. So E was basically framed by me. Uh, Actually, it was a totally maths problem I had framed long ago in a mathematical Olympiad. So, all right. Okay. For this, I think I should show some reference also. There is a very good book, uh, Cheng and Mong, basically, I think if I recall the name correctly. This is the combinatorics book. You may love to, if you are a maths lover, you would love this book. It's very nice book for combinatorics actually. So basically, I have two types of proofs. One is through reflection theorem. Other is just normal method you all used for finding this exactly. So reflection theorem, I will prove. I will just show the proof of reflection first of all from this book, and then I will continue the reflection theorem proof. Second, just normal proof. I'm just doing right now. Right. So let's begin. The problem says that journey begins from 0 comma 0 to x comma y. At any point x dash comma y dash on my path, I can either leap to rightward to x dash plus 1 comma y dash or upward. So basically, you have to go either right or go up. Okay. So you can take just path like this. Okay. Now, so right, so you have to count all the path. Basically, count of basically x should be the sum of all the fp over all points p in the S. Okay, whatever points you take in the whole grid. This so we are placing this rectangle on the coordinate plane. Let's bottom left corner to be the origin. Okay. Now, suppose p is any point I comma j. If the path, suppose understand this, like I draw a vertical line here. If path crosses x is equal to I at point, suppose I comma x, it should definitely cross I minus 1 comma x, right? Because the path can go, it can go just like this, then this, right? So if it's crossing there, definitely it must have crossed this point, right? Is it clear? Okay, so that can be done. So wait. Okay. So which can, so we are, if path press, then what I'm doing, so if path first crosses x is equal to I at point, suppose I comma x, then it should have definitely passed I minus 1 comma x. So this can be done in I minus 1 plus m minus x. Cm minus x ways, right? This is clear. Basically, I should write it well. Okay. Then from I comma x, there are x plus n minus I, Cx ways. This ways to travel to n comma 0. Fine. Okay. So we basically need to evaluate x is equal to 0 to j minus 1, j is equal to 0 to m, and I is equal to 0 to n. That's all. Times of I minus 1 plus m minus x, Cm minus x, n minus I plus x, Cx. Okay, so for each point I comma x, there are m minus x choices for j, right? For each path can cross through that point. So we can basically simplify this sum as follows. Which will be equal to this summation okay. So basically we have to find this whole thing at the end. This much is clear to all. Oh, again screen is not visible. Now is it visible? Hello. Okay. So what all you all missed, I basically was not seeing the chats. Wait, let me. Okay. This basically you all saw this triple summation. I converted into single summation. Is it still not visible? It's visible, right? Okay. So you all saw this proof from triple summation. I converted into single summation, right? This much. So I can go ahead. So from here, basically, I want to show some mathematical stuffs like there's a theorem called Vandermoot's theorems in combinatorics. Okay. So uh, okay. So is the book visible on the screen? Uh, is it visible, the Vandermoot's identity? Okay. So basically, this is the wonder. I think if you would have prepared during JE times, this or maybe Olympiads. So this is the whole proof. Actually, I think I need not write it here. So summation of mi and r minus I is get converted into m plus n cr. Okay. This is the whole proof. I mean, if you need, I will share this whole book with you. Okay, this is page number 74 in the book. So we'll use this Vandermont's identity. I'm not going to prove it. You can see the proof yourself. Okay. So let me go back to okay. Right. So this whole summation from the Vandermonts get converted into basically. So you see, I think I messed up somewhere. Mm, mm, mm. Uh, Wait, this should can't be a single summation actually. Wait. Okay, so m minus j term I missed actually. That's what I was thinking. So uh, can I just how do I copy it actually? Okay, fine, I'll just write it again. So basically, there was summation j is equal to 0. J is equal to 0 to m. I is equal to 0 to n. M minus j times of I minus 1 plus m minus j c m minus j n minus I plus j cj. Okay, that will be basically summation of j is equal to 0 to m m minus j times of summation of I is equal to 0 to n I minus 1 plus m minus j c m minus j times of n minus I plus j cj. That's all. Okay, now you see, the inner sum is just basically you see like this x of m minus j y of j. You saw wonder wands, right? So it's over all x plus y equals to m plus n minus 1. So by Vandermonts, this will be equal to m plus c, m plus n, c m plus 1, basically. M plus 1 times of m plus 1 c2. So the answer turns out to be m plus n c m plus 1 times of m plus 1 c2, which is equal to mn by 2 m plus n cn. That's all. Is this fine? Oh, screen again is sharing. Hello, is am I visible right now? Actually, uh, in my hostel, there's a power cut, so right now just internet went off. So I think again I will have to screen share. So we had almost completed the proof for the basically kind of brute force, we can say, not exactly brute force, but okay, the normal maths method. Let me just keep it here so that I can see the chats actually. Right. Okay. Right. So this is fine. I had a second method I'm not sure how much you all saw this whole proof. Did you all see the whole proof? I will basically share this whole slides with you all once I end the session, so it will be fine. Basically, I will type it out and say. So there is another proof that is by reflection principle. Okay. So basically, for each point p I comma j, reflect it over the center of the grid. For a path okay. So okay, wait, I had right. So I'm giving a formal proof of this problem through reflection principle. See, the setup is same. Place the rectangle on the coordinate plane with the bottom left corner at the origin. Suppose there is a point p I comma j. Okay. So t be some path. T be some path from the top left corner to the bottom right. Okay. And we call an ordered pair p comma t good if t does not pass through p or any point above p. All right. Okay, that is fine. Now let p dash comma t dash be the reflections of I minus 1 comma j minus 1 and t over the center of the grid. Right. Okay, so p lies if p lies to the bottom, suppose if p lies to the bottom or any left edge of the rectangle, then fp will be definitely 0, right? Because we have defined p like that. So if p lies anywhere fp should be 0. Otherwise, either of pt or p dash comma t dash can be good, a good path. Okay, since t passes through either of the region of the points above and to the right of ij, so yeah, or regions of points below and to the left of I, basically I minus 1 comma j minus 1. So if exactly one of the p comma t or p dash comma t can be good. Okay, so there are basically mn times of m plus n cm pairs of pt with p not lying to the bottom or left edge of the rectangle. So I'll just write it down here. Okay. Such that P not lying anywhere to bottom or left edge, maybe left edge of the rectangle. So total good pairs will be right. So for understanding this reflection principle, basically this solution through reflection, you have to go through the reflection principle actually. So I'll just show which page number or where it is. I think it was near page number 90. There was just like this. When you go through these sorted path chapters here, okay, you see reflections principle here. The number of shortest path routes from P to Q that meet the line L is equal to the number of routes from P dash to Q. You just reflect P to P dash, and both will be equivalent to the number of paths. You see the proofs here. You can go through the proofs. There is an amazing problem that is Catalan problem. It often come in the mathematical Olympiad. I remember it was in more sometime ago. So amazing proof on Catalan is given. So I don't want to go much in details. There are a lot of stuff other than this. So I it makes you to ask me for this book. I'll share this book, and this book is basically you can find on internet. This is Chong and Meng Combinatorics, and very nice book. Other than this, you can find this stuff's reflection principle in the books like Alan Tucker is there. There's very nice book. There's few more on maths. Okay, so okay, right. So I think I can wrap up the session right now. Uh, Thanks a lot for the camp. Thanks a lot for joining the camp. And we have, I think, sent certificates to around 500 or 800 people. We'll send all the certificates by around 2 or 3 days. So this is basically the end of the camp. Fine. Bye.